Hello, I'm going to go over an example of a problem from the first part of the course here. This is going to talk about normal distributions and reading histograms and things like that. It's also going to talk about discrete and continuous variables here. So um, again, we always want to make sure we show all our work, clearly indicate our methods because we're going to get scored on our methods as well as the correctness of our work. So the following histogram shows the relative frequencies. So the first thing that we have to remind ourselves of is this relative frequencies piece. Okay, right here, relative frequencies. That means it's going to be the percentage. That means we're going to deal with the percentage of each one instead of actual counts. Recorded to the nearest inch. So it's going to record to the nearest inch. So if they do that, then we're talking that this is now going to be a discrete random variable because we don't have like 3.5, all right, in a population of women. So we're talking about a population of women. So the mean of the population is 64.97 and the standard deviation is 2.66. So understand that this is a population of women. This is not a sample of women. Now that we know all about samples and sampling distributions and all that kind of stuff, this is just a population of women. We're going to use this. So we know this is the standard deviation. So we know this is the typical distance or typical number of inches a typical woman is away from the mean. The mean is 64.97. So this is the typical height, but this is the typical distance away from that height. So we would not be, 2.66 inches away from 64.97. Isn't that strange? Notice that we're rounding everything else to the nearest inch. The height's to the nearest inch, but the mean and the standard deviation are rounded to the nearest hundredth here. All right, so here's our histogram, or here's our histogram. Now they tell us little numbers on top. So this is 1% of the population is at 58 inches, 2% of the population is at 59 inches, 3% is at 60 inches. So altogether, if we think about adding this up, this is 6% is 60 and below. So just kind of getting your orientation on here. Here's 64, somewhere in the middle here. We said 64.97. That would round to 65. So you see how that is kind of the most frequent. We see the data piling up around 65. So it says, based on the histogram, what's the probability that a selected woman would have a height of at least 67 inches and show your work? Okay, so how are we going to show our work here? Because it's kind of obvious that at least 67, that means that she could be 67 inches tall, and she could be 68 inches tall and 69 inches tall. Those are all at least 67. So how are we going to show our work there? We're going to do it kind of quick, okay? We're going to say that the probability of a woman at least 67 inches tall is equal to the probability woman that the height equals 67 plus the probability that the height equals 68 plus ... plus the probability that the height equals, and then the last one is 72 inches. So then now we have to show that. So this is equal to the, we have 0.11 plus the height of 68 right here is 0.07. So 0.07 plus ... plus, and then we just have to show them kind of our methods. We don't have to waste all this time actually writing out each one of those. Now we go to our calculator and we add them up, or we just add them up in our heads. Let's see, 1, 2, 3, 4, 9, 16, 26, 27. So 0.27. So that's how we would show our methods, and that's how we'd get our full credit for number one. That's the probability that if you select a woman, she's at least 67 inches tall. All right. So that's just, and because it's discrete, okay, because we have a percentage for each one of those heights, we just add those percentages together. Okay, if you think about in a continuous situation, we wouldn't have these bins so clearly defined, and we wouldn't have these pieces. It would just be a distribution, and we'd be able to find the area under these curves. All right, what is the area under the bar corresponding to 67 inches? Well, it's the width is 1 and the height is 0.11. So the area is equal to 1 times 0.11, which is 0.11. And what does that represent? Okay, what does that represent? That's the percent. Oops, sorry. Okay, what's that represent in terms of probability? That's equal to the probability that a woman is, that height is equal to 67. That's the probability that a woman is, that it is equal to 67. All right. Then it describes so part C, it displays a discrete probability model for height. However, height is often considered a continuous variable, right? Because there are lots of variations. It's not just people don't grow in 1-inch increments. And then it says, consider a normal model that uses the mean and standard deviation for the population as its parameters. Okay, so that's just that's not asking us a question yet. In I, use the normal model in a relationship between area and relative frequency to find the probability that a randomly selected woman will have a height of at least 67 inches. Okay, so then now what they're saying is turn it into a continuous, oops, that doesn't work. Turn it into a continuous model. See how this does. Yep. So now we just have a curve. We know that the center is 64.97, and we know the standard deviation is 2.66. And here, I would always draw, if you can do it, draw that picture to support your work. So that's a picture of how that's going right there. So in order to get that area under a normal curve, we need to get its z-score. So the z-score for 67 height would be 67 minus 64.97 divided by 2.66. And let's just get that on the calculator quick. 67 minus 64.97, and then divide by 2.66. So again, we're figuring out how many. So 67 is 0.76 standard deviations above the mean. So 0.76 standard deviations above the mean. So in the normal distribution with 0 as its center and 1 as its standard deviation, this spot right here, 0.76, this area right there and this area are exactly the same. The z-score links up those two pictures. So now we're going to go on to, let's get rid of this. So now we need to come up with that probability. So we're going to look that up in a table or use our normal CDF from our calculator, or I'm going to use a normal probability calculator. All right. The mean is 0. If I'm going to use z-scores, the mean of z-scores is 0. Standard deviation is 1. I want to find out the probability above, and I have a z-score of 0.76. Enter. And it tells me the probability is 22.36. 22.36, so 0.2236. So the probability that the height is greater than or equal to 67 is equal to the probability that we find a z-score that's greater than or equal to 0.76, which is equal to 0.2236. So if it was a continuous model, if we treated it like a continuous model, then we'd be talking about that angle. And you would, again, use your calculator to come up with that value. All right, whoops, come on. I wonder if I can hit the down arrow. I can. Good. All right, consider normal. We just did that, show our work. Do your answers in part C, I, and A match? Well, I don't remember what our answer was up here, so I got to re-add it. So 11, so 18, so okay, 1, 2, 3, 4, 9, 16, 27. Ooh, isn't that exactly the same? Why would it not be? Well, here you go. So they're not exactly the same. No, the discrete model is it has more probability, gives a higher probability. Now, why would that happen? Well, the discrete model, the model that we have is probably not exactly normal. So that's pretty easy. We can just say, the data is only approximately normal. It is likely that the normal approximation will just get us close. Normal approximation will just get us close, okay? So that's not too bad. That's pretty common. I mean, we know that the normal probability, the normal approximation, it's just going to be kind of close. It's not going to be dead on every time. B. So this is a long question, but in 2019-20, we kind of expect a long question on the free response because we know there's only 2 free responses, and they're expecting us to spend 25 minutes on one of them and 15 on the other. So we can kind of expect to have lots of different parts in one of those questions and kind of drawing in lots of different ideas. All right, part D, let the random variable H represent the height of women in the population. The probability of height is less than or equal to 60 represents the probability of randomly selecting with a height less than 60 inches. Based on this information, give the probability can be found using either discrete model or normal model. Give an example of a probability of H that can be found using the discrete model, but not in the normal model. Okay, so in the discrete model, the probability that H is equal to 60 can be found. We know that because in that discrete model, there's a bar at 60 with a width of 1 and a height of well, if we go back and look at the point, 0.03. That bar has a point of 0.03. Oh, let's do this. There we go. So 0.03. So it has an area of 0.03, and that's the probability, 0.03. Okay, but in the normal model, 60, because it's continuous, there's no width to this line. 60 is just, there's width, there's area to the left of it and area to the right of it, but there's no area at that point. So you can't do a specific spot. So probability of H equals 60 in the discrete model can be found, but not in the continuous model. In the continuous model, probability H is less than 60, or probability H is greater than 60 can be found but not probability H is equal to 60, okay, right there. So again, because there's infinitely many points around here, no matter how many points are lined up at 60, the probability of hitting 60 exactly is technically 0. Okay, give an example that can be found using the normal model, but not the discrete model. Explain why. All right. Well, in the discrete model, so in the discrete model, we only have, now that the black marker writes nice, but erases terrible. All right, in the discrete model, can we find the probability? Well, in the continuous model, we have continuous things that we can find. So we can find the probability that the height is between 63.2 and 63.8. Okay, we can find this probability. That can be found in the continuous model, but not in the discrete model. Okay, and the reason why is that we don't know we know the probability, let's see, in the discrete model, we cannot use decimals. The model does not have enough what we call precision. Doesn't have enough precision. We can't see how many. They just kind of lump all those together. We don't know what this looks like in here. Okay, we don't know what this looks like in here. So in this gap here, we don't know how high that part goes. We just know the whole bar goes up. Okay, so there's not enough precision in that model. All right, that's long enough for this one. We'll go forward into, we'll keep these videos coming for you in the future. You can see that we're going to go on to number 3. I'll give you a preview of number 3. We're going to be talking about a spinner, and so we're going to get some probability into this. So I'm going to stop.